Let us now try to understand the concept, the fundamental behind turn planning. Unlike road vehicles, a ship does not turn sharply, reason being lesser friction offered by the water and also the influence of momentum. Whenever the vessel alters its course, the vessel actually moves along a curved track which can be treated as an arc of a circle. Let's try to understand this using a diagram. Let us assume that this is the initial course of the ship. You can follow the laser pointer. At this particular point, we have a course alteration. This is point delta. So at this particular point, the vessel has to alter its course, and this is our final course. Now, even though the courses are shown as straight line tracks and the course alteration is shown at point delta, the vessel will not move along these straight line track while it is altering its course. Vessel will be moving along the arc of a circle, basically the turning circle of the ship. Let us now show the curved path on which the ship actually move. You can see this maroon color arc. Now this is the actual track on which the ship will be moving when it is altering its course. The vessel will be initially moving on the initial course up to this particular point, that is this tangent point of the arc. And after this point, the vessel starts to travel on the curved path and it follows the curved path up to this point here, which is again a tangent. The final course is tangential to the turning arc here. And from this point onwards, the vessel again starts to move on a straight line track, which is the final course of the ship. आप एक Now, in case of small ships, these arcs are also small. In case of a small vessel, the arc could be much smaller with a much smaller radius, as the turning circle of small ships are much smaller. But for large vessels, these arcs assume greater radii. Now, for a large ship having a larger turning radius or a larger turning circle, the track on which the ship will be moving will be this one. So for larger ships, these arcs on which the ship moves when it is altering its course assume greater radii and they need to be treated differently. We can also easily find the center of this turning circle or center of this arc. In the coming slides, we will be seeing how do we identify the center of the turn, how do we mark this curved path on our chart. So let us, for the time being, show the center of the turn. You can see this is the initial point A. The vessel moves on the initial course up to point A. From point A, it starts to move on the curved path. It moves on the curved path up to point B. And from point B, Bravo point, it starts to again move on a straight line track, which is the final course. This is the center of the turn or the center of the turning circle represented by C, and Charlie to Alpha or Charlie to Bravo represents the radius of this turning circle. For a small ship, the radius will be smaller and you will have a small arc like this one. But for a bigger ship whose turning radius is bigger, you will have a greater radii arc like the Alpha Bravo AB arc shown on the screen. Now for small ships, if you look carefully, the arc is not much far away from the straight line tracks. But as the size of the ship becomes bigger and bigger, the turning radius becomes bigger and bigger, these arcs are at a substantial distance from the straight line track. Now it is possible that the straight line track of the ship may be following or going through a safe path, a safe passage, but this curved path may be passing over a danger. So it becomes very important for us that whenever we are planning our passage, we mark these curved paths on our chart or they are marked on our ECDIS, and we check the safety of the curved path because this is the actual path where the ship will be moving. The vessel will not be moving on straight line track from alpha to delta and delta to Bravo. It will be moving along this arc alpha to Bravo. So it becomes very, very important to check the safety of the passage along this arc and ensure that the curved path is not passing over any shallow patches or navigational dangers. So this is the importance of planning a turn in a passage plan. We need to identify this curved path on our chart or on the ECDIS. We need to check the accuracy. We need to check the safety of this curved path, that it is running through safe waters, not running over shallow patches or navigational dangers. Now, the first concept which we need to understand for the purpose of turn planning is the derivation of the rate of turn formula. So let us try to understand how do we derive the rate of turn formula. We have seen this particular ship moving on the initial course up to point A, then moving on the curved path from Alpha to Bravo, and then moving on its final course. Let us assume that the radius of this turn, which has been planned for this particular ship, is R. So let us represent Alpha to Charlie, which is the radius, as R. The Charlie to Bravo radius will also be R. Let us also assume that the angle by which the vessel is turning is theta degrees. So this angle represented by this yellow shaded portion by which the vessel is turning is theta angle. The vessel is moving on the arc from Alpha to Bravo. Now, by the definition of an angle in radian is basically the ratio of arc of a circle to the radius of a circle. Using this definition on our course alteration angle theta, the angle theta in radians should be equal to the arc, which is alpha Bravo, divided by the radius of the turn. Now this distance alpha to Bravo or the arc alpha to Bravo can be easily obtained by using the formula distance is equal to speed into time. The speed of the ship, let us assume the speed is V knots and the time taken for the alteration is T hours. The time has been taken in hours here because the speed is given in the units of nautical miles per hour. So time has to be used in hours. Divided by the radius of the turn, the radius will be in nautical miles. Now in this formula, we would like to see the angle in the format or in the units of degrees. Degrees is the unit which we normally use on a ship. We do not use the radians. So we would like to see the angle here in degrees, and also the alteration of a ship is done in a matter of minutes, not in hours. So we would like to have the time here in minutes instead of hours. So let us convert these radians to degrees and hours to minutes. For that, we should be aware of that 1 radian is equal to 57.3 degrees. So in this formula, instead of writing the angle in radians, I want to input my angle in degrees, and this angle input in degrees divided by 57.3 gives me the same value as the angle in radians. Going to the right hand side, we have the speed V in knots multiplied by time t in minutes. So this time has been converted into minutes now instead of hours, and this t minutes divided by time in hours. So in the denominator, we have the radius as usual in nautical miles. So you can now see radians have been converted to degrees and the time has been converted to minutes. Now what we do is these t minutes term is taken to the left hand side. It comes in the denominator here. So theta degrees upon t minutes is equal to V naughts multiplied by 57.3. This 57.3, which was at the denominator on the left hand side, is now taken to the numerator of the right hand side. So V naughts multiplied by 57.3 divided by R in nautical miles multiplied by 60. Now the term which you see on the left hand side, that is theta degrees divided by t minutes. Theta is the angle by which the ship is turning and t is the time which the ship takes to complete the turn or the alteration. This is what is known as the rate of turn of the ship. So rate of turn is equal to degrees by minutes. These are the units of rate of turn. The ship is turning at a rate of so many degrees per minute. This will be equal to V in knots divided by the radius in miles. V is multiplied by 57.3. Radius at the denominator is multiplied by 60. Now, if you look carefully, the numerical terms which we have on the right hand side, 57.3 in the numerator and 60 in the denominator are close to each other. So these terms being close, without any appreciable loss of accuracy, these can be cancelled out and the formula gets simplified to the rate of turn equal to V upon R. This is the rate of turn of the ship in degrees per minute. This is the rate at which the ship is turning and it is equal to the speed of the ship in knots divided by the radius of the turn in nautical miles. Now see the practical relevance of this formula. How does it help us in actual situations, actual scenarios on board? Let us understand this using an example. We have a vessel which is moving on an initial course of 010 degrees true and the final course is 080 degrees true. She is doing 15 knots of speed and she intends to turn about an island or islet keeping a distance of 1.5 miles. So basically 1.5 miles is the radius of our turn. We need to find out what will be the rate of turn and how long will the ship take to complete the turn. So let us try to solve this using the concept of rate of turn what we have understand till now. So let us first make a diagram of the situation of the data which is given to us. You can see the diagram on the screen now. Vessel is moving on a initial course of 010 degrees and the final course is planned to be 080 degrees and the vessel has to make the turn about an island. Let us assume we have the island here at this particular location, which will be the center of our turn. And the radius of the turn is assumed to be 1.5 miles. So you can see the radius of the turn, Charlie to Alpha, denoted as 1.5 miles. Then Charlie to Bravo, denoted as 1.5 miles. So let us now apply the formula and see what results do we get from there. We know from the rate of turn formula, rate of turn is equal to V upon R. The speed is given to us as 15 knots and the radius of the turn is given to us as 1.5 miles. So this tells us that to execute this turn, the vessel needs to maintain a rate of turn of 10 degrees per minute. So the first thing which can be done is we can evaluate whether the vessel is able to do or achieve this much of rate of turn or not. This may be very easy to achieve on a small ship or a medium-sized vessel, but it may be difficult to achieve if you are on a very large ship. So this is the first utility of the formula. We get a value of the rate of turn and we can evaluate whether this turn will be executable or not. Now we know that the vessel's rate of turn needs to be 10 degrees per minute to execute this turn. The amount of alteration which we have is 70 degrees. Initial course is 010 and the final course is 080 degrees. So vessel has to alter by 70 degrees. Now the vessel is altering 70 degrees at a rate of 10 degrees per minute. So the total time which the vessel is going to take is 70 degrees divided by the rate which is 10 degrees per minute, and it comes to 7 minutes. So from point alpha, when it starts to move on the curved path, up to point Bravo, when it reaches on its final course, the vessel is going to take a total of 7 minutes to complete the turn. So we know what is the rate of turn required. We also know what is the time which the ship is going to complete the turn, giving us an understanding of the turn, and we can now easily plan this turn if these parameters are within our control or they are achievable. Planning a turn. By planning a turn, we mean what is the way or the method to plot or have the curved path on which the ship moves while it is altering on our chart. Now this planning of turn may be required in different scenarios. Depending upon where the ship is, we may be in restricted waters and we may be planning a turn around an object. We may have a lighthouse, a land's end, or a island around which the vessel is turning. Or there could be another scenario, another situation where the vessel is turning in open sea. So we will see the planning of turn in different scenarios one by one. Let us first go into the option where we have a object which is visible to us or a object which is radar conspicuous at the center of our turn, and we are turning about that particular object. It could be a lighthouse, it could be a land's end, or it could be an island. So let us have an example area here. You can see our vessel is in this particular area of the chart, and we have a lighthouse here at land's end at this particular point. You can follow the laser pointer. Let us represent that lighthouse as C. We want to have this lighthouse as the center of our turn. Now let us assume the vessel is right now at this particular position. This is the initial position of the ship. And let us assume that the vessel needs to go to this particular position. You can see the final position also coming up on the screen. So we are at our initial position right now and we want to reach to our final position, making an alteration around this land's end or land's edge, having our center at this lighthouse point Charlie. Now the first step which we need to take is to assume a radius. We have to decide on a radius which we want to keep while making the alteration. Now the navigator will need to decide the radius basis different factors, which will be vessel size, the draft of the ship, what are the weather conditions in this area, is there any proximity to navigational dangers, what is the traffic in this area. So basic all these data items, the navigator will fix up a particular radius which he wants to keep, or you can see he will fix up a minimum distance which he wants to maintain from the land. Now once the radius is finalized, with C as the center and draw an arc. So let us show the planned radius here. You can see this radius coming up on the screen represented by R. This is our planned radius. So we open up our compass equal to our planned radius. We center our compass at point C and we draw an arc. You can show the radius here also. Now with compass centered at C, radius equal to the planned radius, we draw an arc. You can see the maroon color arc now coming up. This is the curved path on which the ship will be moving while it is executing the turn or while it is altering the course. Now what we do is, from our initial position, we draw a tangent to this arc. So using our scale parallel ruler, from our initial position, I draw a tangent to this arc. You can see the tangent coming up. It touches the arc at this particular point. Let's name the point as A, alpha. Now this becomes our initial course. From our initial position to point alpha, this represents our initial course. Now the same thing is done with our final position. We now draw a tangent to this arc from the final position. So using our scale or parallel ruler, we draw an arc. We draw a tangent to the arc from our final position. You can see the tangent coming up. The tangent point is here at this particular location. Let's name the tangent point as B, Bravo. Now this line which you see, the tangent line which you see from the final position to Bravo, this represents our final course. So the vessel moves on the initial course, that is the first tangent, goes up to point alpha, point A. After point A, the vessel moves on the curved path, that is on arc alpha to Bravo. From point Bravo, the vessel moves on the final course. So the turn has been planned and plotted on our chart or ECDIS. So this is the method to have the curved path on our chart. When we have a object which is visible to us or a object which is radar conspicuous, using that object we can plan our turn and we can find out our initial and final courses. Now in an open sea, obviously we will not have a reference point at the center of our turn. So the method of planning a turn, method of having this curved path on our chart is different from what we had in restricted waters or when we had a object which was available to us at the center of the turn. So in this case, we will have to draw the initial and final courses first. So without bothering about the center or the curved path, we first draw our initial and final courses. So let's plot our initial and final courses in the diagram. You can see the initial course, the alteration point at delta, and the final course coming up in the diagram. Now we have to choose a suitable radius. The radius is decided as per the ROT formula. ROT is equal to V by R. So a convenient radius with which we have a achievable rate of turn is selected by the navigator depending upon the size of the ship, the loading condition of the vessel, the weather conditions. And once the radius is finalized, we can now move on to plot the curved path. First of all, we pick any convenient point on the initial course, any convenient point of our choice. Let us assume that we have picked this particular point here and named it as P, Papa. Now we open up our compass equal to our planned radius. The compass is opened up equal to our planned radius and placed at this point Papa. So centered at point Papa, radius equal to our planned radius. Using the compass, we draw an arc. You can see the arc coming up on the screen. Now we have to draw a tangent to this arc, and the tangent should be parallel to the initial course. So using our parallel ruler or sliding ruler, we align it with the initial course, transfer it to the arc, and we draw a tangent. You can see the tangent now coming up in the plot. Now the same thing is done on the final course also. We pick up any convenient point on the final course, any convenient point of our choice. Let us assume we pick up this point here, point cubic, Q, and we open up our compass equal to the planned radius. Centered at point Q, radius equal to the planned radius, we draw an arc. You can see the arc also coming up. Now we align our parallel ruler to the final course, transfer that ruler to this arc and draw a tangent. So you see the tangent to the second arc coming up. This tangent is parallel to our final course. Now the point where both these tangents intersect, intersection point of the tangent is the center of our turn. So this point is named as C Charlie, and this particular C point is the center of our turn. Now you can pick up the compass again, center the compass at point Charlie and draw an arc. So centered at point C, radius equal to our planned radius, we draw an arc. You can see the arc coming up on the screen now. You will see this arc will be touching the initial and final courses, depicting the curved path where the ship is going to move. So you can see that we did not have a reference point at our center, and using this technique we have obtained the center of our turn, and we have also plotted the curved path on which the ship will be moving. Now we have seen the planning of the turn in different scenarios, how to plan the turn and how to have the curved path plotted on our chart. Now the next challenge which comes in front of the navigator is to monitor the progress of the ship when it is moving on the curved path. As discussed earlier, we can easily monitor our progress while moving on the straight line track up to point alpha on our initial course. We can use many different techniques like parallel indexing, having a look or monitoring the cross track of the ship, and we can monitor the progress. Likewise, once the ship has completed the turn and after point Bravo it starts to move on the final course, again it's a straight line track and it is easy to monitor the progress. We are going to see now how to monitor the progress of the ship from Alpha to Bravo when the vessel is moving along the curved path or on the arc of the circle. So this also may be required in different scenarios. We may have a object visible to us at the center of the turn. It may be a radar conspicuous object, or we may need to monitor the progress in open sea conditions when there is no reference object available to us at the center of the turn. So let us see one by one in different scenarios. How can we easily monitor the progress of the ship along the curved path? First, we are picking up the situation where we have a visible object at the center of our turn. So this particular lighthouse object at sea is visible to us. Now for monitoring, we use a simple fact that the radius of a circle is always perpendicular to the tangent of the circle. Now the bearing of the lighthouse, whenever the ship is moving on the curved path, the bearing of the lighthouse always represents the radius of the turning circle, and the fore and aft line of the ship represents the tangent to this turning circle. So the fore and aft line and the bearing of the lighthouse should remain at right angles. Let us understand this from the diagram. When the ship is proceeding on its initial position, the vessel reaches at point A. You can see the vessel being shown at point alpha. Now, when the vessel is at point A, this lighthouse will be exactly abeam of the ship. It will be abeam of the ship. The fore and aft line of the ship represents the tangent to this turning circle. You remember the initial course was drawn at a tangent to the turning circle. And the bearing of the lighthouse represents the radius of this turning circle. Both are at right angles, 90-degree angle. So that means the lighthouse would be abeam. Now, as the ship progresses along the curved path, let us assume that the vessel comes at this particular location. The fore and aft line represents again the tangent to the turning circle. And if you draw the bearing of the lighthouse, it represents the radius of the turning circle. So again, it should be at right angles. That means the lighthouse should be a beam. As the ship progresses further and reaches at this particular point, again, the fore and aft line is tangential, bearing of the lighthouse is the radius. Both are at right angles, so lighthouse should be a beam. And eventually moving to point Bravo, again we can see the fore and aft line is the tangent, bearing of lighthouse is the radius, both at right angles, so lighthouse should remain a beam. So you can see at all these intermediate positions, if the lighthouse stays abeam or very nearly abeam, it ensures that the vessel is moving on the planned curved path. Hence, for the vessel to remain on the curved track, the object C must remain abeam or very nearly abeam. Now, during the alteration, if at any time you observe that the object is no more abeam and it has now started falling abaft of the beam, this means that the vessel is going outside the arc or the vessel is turning slowly. Let me show you this in the diagram. If the lighthouse starts to fall abaft the beam, it indicates that the vessel is not moving on the planned arc but moving on this particular dotted line track. So you are moving outside the arc, the vessel is going outside the arc. If the vessel goes outside, you will observe that the lighthouse will start to fall abaft the beam. This means that the vessel is turning slowly. The rate of turn needs to be increased by giving a greater helm angle. So at any point of time, object falling abaft the beam tells you to increase the rate of turn and bring it abeam again. And if at any point of time you find that the object is moving ahead of the beam, then in that case, the vessel is moving on this dotted line track. If the object falls or moves ahead of the beam, vessel is going inside the planned arc, or you can also say she is turning too fast. The rate of turn needs to be reduced by easing the helm. So a very good indication to monitor the progress, keeping the lighthouse, which is at the center of our turn, exactly abeam. Whenever it starts to fall abaft the beam, we are turning slowly, increase the helm angle, increase the rate of turn and bring it abeam again. And if at any point of time it moves ahead of the beam, that means we are turning too fast, reduce the helm angle, reduce the rate of turn and bring it abeam again. Ensure that the lighthouse remains abeam till the time you reach at your final course, that is at Point Bravo. After Point Bravo, the curved path is completed and the vessel starts to move on the final course on a straight line track. Execution as well as monitoring of the turn when we have a visible object available at the center of our turn. Assume a different scenario. Let us assume that the object which was supposed to be visible to us is no more visible because of restricted visibility. So we are not able to observe that object. So we cannot observe whether it is a beam or above the beam or moving ahead of the beam. So in this kind of a scenario, the object will still be available on the radar. So we have a radar conspicuous object available to us. Now, how can we monitor our progress on the curved path using this radar conspicuous object? Now for this, a very simple way, a very simple technique is to set up a VRM. Set up a VRM around the ship with radius equal to our planned turn radius. So we have planned our turn using radius R. Using the same radius, we set up a VRM on the ship when it is proceeding on the initial course. So the VRM is set up. Now while moving on the initial course, as soon as the vessel reaches at point A, we will observe that when the vessel reaches at point A, this is the point where the VRM which we had set up is passing exactly over the center of our turn. Before reaching point A, the lighthouse or the center of our turn will be outside the VRM. As soon as the vessel touches point A, the VRM is exactly passing over the center of our turn or over this radar conspicuous object, indicating to us that we need to start the alteration and vessel needs to start moving on the curved path now. Now moving ahead on the curved path, as the ship proceeds ahead at this particular location, we have to ensure that this particular lighthouse, the radar conspicuous object, it always stays on top of the VRM. It should neither come inside the VRM nor go outside the VRM. We should ensure that this center of the turn or the object remains exactly on top of the VRM. Again, when the vessel reaches here, we ensure that the object is on VRM, and when the vessel reaches at point Bravo, again we ensure that the object stays exactly on top of the VRM. Now, at any point of time during the alteration, moving from Alpha to Bravo, when the vessel is moving on the curved path, if you observe that the lighthouse has gone outside the VRM, the object has fallen out of the VRM. This indicates that the vessel is going outside the turning circle arc or she is turning slowly. And this indicates that the rate of turn needs to be increased by giving a greater helm. And also, if at any point of time you observe that the object is falling inside the VRM, the lighthouse has fallen inside the VRM, it indicates that the vessel is going inside the planned arc or she is turning too fast and the rate of turn needs to be reduced by easing the helm. A very simple way, a very simple technique, only using the VRM of the radar to find out whether the vessel is moving on the curved path or not. So a very easy way to monitor our progress with a radar conspicuous object. The next scenario, if we do not have a radar conspicuous object also, we do not have a visible object, we do not have a radar conspicuous object, then the option which is available to us to monitor our progress along the curved path is by using the EGDIS. As per the minimum performance standards for the EGDIS equipment, it is possible to draw both straight and curved segment of courses on the EGDIS. EGDIS also provides us with a real-time position fixing. Hence, the navigator knows where the vessel is at any particular moment. Rather than the situation on paper charts, where we had our positions coming later on. The position when it is plotted on the chart is not the real time position. It was a previous position. On axis, we have a real time position. So you have the curved path being shown on the axis. You have the real time position of the ship being shown on the axis. And using the axis, you can monitor the vessel's progress along the curved path. On to our next scenario. Assuming that we do not have a axis also accessible to us, we do not have a visible object, we do not have a radar conspicuous object, we do not have a axis. So what can be done to monitor our progress in this particular situation? Now this is where the rate of turn indicator can be used, can be utilized. Now when we had planned the turn, we know what is the speed with which we are executing the turn, with which the ship is moving. We also know what is the radius which has been planned. So speed and radius both are known to us. Now we know the rate of turn formula is equal to V by R. By putting the value of speed as well as radius, we can obtain what is the rate of turn which is to be maintained by the ship. So when the vessel is moving on the initial course and it reaches at point alpha, which is the start of our curved path, we instruct the helmsman to maintain that required rate of turn by using a appropriate helm angle. So the helmsman has to keep a watch on the rate of turn indicator and he tries to maintain the rate of turn as the planned ROT. The helm angle is given accordingly. The rate of turn is maintained as the planned rate of turn, and that will ensure that the vessel should move on the planned track on our curved path. Now this kind of a turn is called as a constant rate turn. This is called as a constant rate turns. It is no more a constant radius turn, but it has converted to a constant rate turn. Now, why is it no more a constant radius turn? The reason for that is if we maintain the same rate of turn, the rate of turn is kept constant. The expression on the right hand side will also remain constant. That is the value of V upon R should remain constant. But we are aware that whenever the vessel enters into a turn, the speed of the ship experiences a reduction. The reduction in speed will vary from ship to ship. It will depend upon what is the rudder angle which has been given, weather conditions, and many different factors. But there is a reduction in the vessel's speed as the vessel turns. Now, if there is a reduction in the speed, since we are keeping the rate of turn constant, the denominator radius is also going to decrease. To keep the ROT constant, if there is a drop in speed, there will be a drop or reduction in the radius also. So this is the reason that this turn is no more a constant radius turn now and is known as a constant rate turn. Now, when we actually practice this kind of execution, what we do to take care of this reduction of radius is practically the rate of turn is calculated for a mean value of the vessel speed. That is mean of the speed at the start of the alteration and the speed at the end of the alteration. We basically make an estimate what will be the drop in speed in this particular situation, and basis that estimate we find out a mean speed. Let us assume if you are entering the turn with a speed of 12 knots and you expect that when you are exiting the turn the speed will drop by 1 knot, it will be 11 knots. So we plan this rate of turn using the mean speed, in this case the mean of 12 and 11, which is 11.5. This value basically corresponds very nearly to the vessel's position midway on the arc. So you will see for some part of the arc, the speed will be more than 11.5, and for some part of the arc, the speed will be less than 11.5, and the vessel will be moving very close to the planned turn. For the initial 50% of the turn, the radius may be slightly more than the planned radius, and for the last 50% of the turn, the actual radius may be slightly less than the planned radius. So it will be having a slight variation from the radius, sometimes slightly greater and sometimes slightly lesser than the planned radius, but these variations are very, very small and they are certainly within a practical and tolerable limit. So this is a constant rate turn, and we can use the rate of turn indicator to execute this turn. We now move on to our next very important concept of the wheel over point and the wheel over line. Now these are very important references for executing a turn. Let us now understand what are these references and how are these obtained. Now the wheel over point is the point on the initial course at which the wheel is put over to initiate the turning of the vessel. Now we have the diagram of this turn on the screen. It is at point alpha when the ship is moving on its initial course and it reaches at point alpha. This is the point where the vessel starts to move on the curved path. Now, as far as the ship is concerned, if you want to start your turning at point alpha, you need to put your helm angle or you need to give the helm order slightly before this particular point. Now, why do we need to give the helm angle slightly before this point alpha, before reaching this point alpha? The reason for that is that every vessel takes a certain time to respond to the helm angle. This is called as a reaction time. When the wheel is put over, a particular helm angle is given. The vessel does not start to alter its course immediately. It waits for some time, takes this time to respond, and then starts the alteration. Now this time which the ship takes is called as the reaction time of the ship. And the distance which is covered by the ship during this particular time is called as the reaction distance. This reaction distance is denoted by alphabet F. As per our convention, alphabet F, foxtrot, represents the reaction distance of the ship. So if you want your ship to start making the alteration at point alpha, the helm order needs to be given reaction distance before reaching point alpha. So wheel is to be put over when the vessel is reaction distance away before reaching at point alpha. Let us assume for this particular ship, this much is the reaction distance. You can see this green color line showing the reaction distance for this vessel. The point at the end of this reaction distance, represented by W, is our wheel over point. So alpha to whiskey, A to W represents the reaction distance, and this reaction distance is denoted by alphabet F, foxtrot. So when the vessel is moving on its initial course, it reaches at the wheel over point whiskey, the helm is put over, helm order is put over. Vessel takes this much time and distance, whiskey to alpha, to respond to the helm. After this much time covering distance whiskey to alpha, the vessel responds and starts making an alteration and finally reaches at point Bravo, completing the turn. Now, how do we find out or determine this reaction distance for the ship in a particular situation? This reaction distance depends upon various factors like the size of the ship, the loading conditions of the ship, whether the vessel is loaded or in ballast, It also depends upon the trim of the ship, what is the type of the ship, block coefficient, size of the rudder angle given, all these different parameters. Now, this reaction distance can be obtained from the maneuvering characteristics booklet. Most of the new building ships, this is available in the maneuvering characteristics booklet. And in case not available, this reaction distance F can be taken as a general common value of 0.1 nautical miles for small ships, 0.15 nautical miles for medium-sized vessels, and it can be taken as 0.2 miles for large vessels. These are the general figures which can be taken for reaction distance F if it is not available in the maneuvering characteristics booklet of the vessel. So 0.1 mile or 1 cable for small ships, 0.15 miles or 1.5 cable for medium ships, and 0.2 miles or 2 cables for a large ship. Now there is no definition for small, medium and large vessel. You will have to fit your ship in one of these categories and then pick up these values of the reaction distance to be used to identify the wheel over point. Now this wheel over point is a very important reference as far as the turn planning is concerned, because this wheel over point basically tells us what is the exact moment where the wheel should be put over and the turning of the vessel initiated. If you apply the helm before reaching at the wheel over point, the vessel will turn on an arc before the actual alteration, and it will have a cross track error when it reaches on the final course. The same thing happens that if you give the helm angle or the helm order after crossing point W, the vessel has overshot the wheel over point. When it reaches on its final track, it will have a cross track error. It will not reach the final course at point Bravo and will instead have a cross track error. It is also going to disturb the nearest distance from the center of the turn. So a very important point for executing the turn. Now we have seen the wheel over point. Another very important reference for us to execute the turn is known as a wheel over line. A wheel over line is a line drawn parallel to the final course and passing from the wheel over point. So we have identified the wheel over point in our plot. If we draw a line passing from the wheel over point and parallel to our final course, so we align our parallelular to the final course, transfer it to point W and draw this line. This maroon color dotted line which you see is our wheel over line. Now let us understand the importance of this wheel over line. In case we have a cross track error, while we are moving on the initial course, we have a cross track error. The advantage of the wheel over line is that there is no need to eliminate this cross track error on the initial course, and we will still be able to reach on our final course with a zero cross track error. So irrespective of any cross track error on the initial course, the usage of the wheel over line eliminates any cross track error on the final course. So let us see it in the diagram. Let us assume that instead of moving on the initial course, our vessel has this much of cross track error and is now moving actually on this particular track. Now, if the wheel over line was not there, the vessel will first need to correct this cross track error, move on the planned track and reach at point W. So vessel will initially give a port helm, reach at point W, then give a starboard helm and start the alteration. Now, if we have a wheel over line And if the vessel is in open sea and this much of cross track does not put the vessel into danger, it is still in safe waters. If the vessel is in restricted waters, this much cross track needs to be corrected. The vessel should have zero cross track error. But if the vessel is in open sea and this cross track error is present, if we have the wheel over line marked, we do not need to correct the cross track error. What we can do is, while moving on this dotted line track, when the vessel touches the wheel over line at this particular point, you can follow the laser pointer. At this particular point, the wheel is put over. The vessel moves this much reaction distance ahead. It will take this much of time and distance to respond to the helm. After this, the vessel responds to the helm and starts to move on the curved path, and you will see the vessel will eventually reach on the final course with zero cross track error. Likewise, you can take another example. If we have a cross track error on the other side, the vessel is on this side of the actual initial course. If it is moving on this particular track, as soon as it touches the wheel over line here at this particular point, you put the wheel over, the vessel moves this much distance, the reaction distance. At this particular point, it starts to respond to the helm, starts to move on the curved path, and the vessel finally lands at this particular position represented by B double dash. And you see that irrespective of any cross-track error on the initial course, the vessel reaches on the final course with zero cross-track error. So this is the advantage of the wheel over line. Likewise, if the vessel was on port side of the initial track, we had a cross-track error towards port, it will be reaching the final course not at point B, but at point B double dash. So this is the only difference, but in all these cases, point Bravo, Bravo dash and Bravo double dash, it will reach on the final course with zero cross-track error. Point. We know how to obtain these two in our plot in that turn. Now in some situations, it may be not necessary to plot the curved path of the ship. If the ship is in open sea, there are no navigational dangers close by, you may decide not to plot the curved path. But the wheel over line and the wheel over point should be marked in all the cases in all the alterations. Because wheel over point and wheel over line are important references which tell us exactly the moment at which the alteration should be started. Now the method which we have seen till now to find the wheel over point and wheel over line is dependent upon the curved path. We have to first plot the curved path. We have to find the center of the turn. We have to find the curved path, and from point A we have to draw the reaction distance to obtain the wheel over point. Now in case we do not need this curved path, or we plan not to make this curved path, we still have a method that without making the curved path, the wheel over line and the wheel over point can be easily identified. This is by using a formula. Let us see this method. The distance between the final course and the wheel over line can be obtained using the formula r into 1 minus cos theta plus f sine theta. R is the radius of the turn, 1 minus cos theta. Theta is the angle by which the ship is turning, plus f. F foxtrot is the reaction distance. Sine theta. Theta again is the angle by which the vessel is altering. So we find out this distance using the formula r into 1 minus cos theta plus f sine theta. Now when this distance is obtained, we now can easily draw the wheel over line. How do we draw the wheel over line? We pick up any point of our choice on the final course. Let us assume that we have picked this particular point. You can follow the laser pointer. This point is picked up on the final course. Now we open up our compass equal to this distance which has been obtained from the formula. This formula will give us a particular distance. The compass is centered at this point. The radius equal to r into 1 minus cos theta plus f sine theta, and we draw an arc. You can see this arc coming up. Now we draw a tangent to this arc parallel to the final course. So we align our parallel ruler to the final course, transfer it to this arc and draw a tangent. This tangent represents our wheel over line. So we have obtained the wheel over line. This formula basically tells us what is the distance between the final course and the wheel over line. Both of these are parallel to each other. Final course and the wheel over line are parallel, and this formula gives us the distance between these two parallel lines. Now when you mark or plot the wheel over line, the point where the wheel over line intersects the initial course is the wheel over point W. So you can see, without marking the curved path, without finding the center, independent of the center and the curved path, we can obtain this distance from the formula, and we can plot the wheel over line, and we can also identify the wheel over point. In case you measure this distance, you mark the curved path also, and you measure this distance alpha to whiskey, you will find that this is exactly same as the reaction distance of the ship, which is used in this particular formula. This will be exactly the same. So whether you find the wheel over point or wheel over line by marking the center, plotting the curved path, and plotting the reaction distance, this is known as the plotting method, or you find the wheel over line by using this formula and plotting it directly. In both the cases, you will obtain the same wheel over line and the same wheel over point. So in situations where the curved path is not required, the wheel over line and the wheel over point can be identified using this formula and plotted on our chart. So this will allow us to have a reference point available to us. We can start our alteration at this particular point, and it will ensure that we reach on our final course with zero cross-track error using the concept of wheel over point. We have the question on the screen now. Your ship's course is 010 degrees true and speed 12 knots. After 6 nautical miles on the present course, as per the passage plan, you have to alter the course to 085 degrees true. Show by a neat sketch how you will execute a constant radial turn if the radius of the turn is to be 2 nautical miles. Now part B of the question says, from the maneuvering diagram, advance is known to be 4 cables. Determine the setting of your VRM, that is the radar VRM, to identify the wheel over point. And the third part, part C of the question says, if the current is setting 315 degrees at a rate of 2 knots, determine the new reference point for executing the turn. And they have mentioned along with the question, use the radar plotting sheet. So this is a practical question picked up from past papers, and this involves the concept of turn planning as well as the concept of how to allow for or how to counteract the current in these scenarios. We have seen the turn planning being done using the ship's particulars parameters, that is the speed of the ship, the radius of the turn, the rate of turn being maintained, but the current was not included. So in this question, we will also see how the current is to be accounted for while planning a turn. Now, before we go into the solution of the question, One thing which is mentioned here, which I would like to take your attention to, is they have mentioned here that the advance is known to be 4 cables. Now, the advance is basically the distance traveled by the ship in the direction of the initial course. Whenever the ship is turning, advance is the distance traveled by the ship in the direction of the initial course before it alter its course by a particular value. We have different advance for different alterations, like advance for 5 degrees, advance for 10 degrees, advance for 15 degrees, and so on. The maximum advance of the ship is attained close to 90 degrees alteration. So you can see the hint also given below. The reaction distance of the ship is also known as advance for 0 degrees. You see, I told you advance is the distance traveled by the ship in the ahead direction before it alters its course by that particular value. So advance for 0 degrees means that the ship has not yet started alteration of its course. That means it is still moving on the straight line, and this much distance has been already traveled. Now after this, the vessel is going to alter its course by 1 degree, 2 degree, 3 degree, and so on. So this advance given here is to be used as the reaction distance, which in this case is 4 cables or 0.4 nautical miles. So let's try to do this question now. They have told us to use a radar plotting sheet. So let's have a radar plotting sheet on the screen. We can see a radar plotting screen. I have zoomed into a particular part so that we can have a clear diagram. So we have the radar plotting screen here. Now our ship's course, initial course is 010 degrees true. Now let's plot the initial course of the ship. You can see the initial course 010 coming up. Now what have I done is I have joined the 190 marking with the center of the radar plotting screen. So telling me that this particular direction is 010 direction. The vessel is moving towards the center of the radar plotting sheet. Now my final course after the alteration is 085 degrees true. So let's show the final course also. You can see the final course 085 degrees coming up on the screen. Now from the center of the sheet, I draw a line joining up to 085 marking. So that gives me my final course. So we have the initial and final courses coming up on the diagram. Now the center of the radar plotting sheet is our course alteration point or the waypoint. Let's name the waypoint as delta. Now we have learned the method of making the curved path. You can pick up any particular point on your final course. Any particular point. I have picked this particular point and keeping my compass at this particular point. Now I open up my compass equal to my radius of the turn, which is given as 2 nautical miles. So I keep my compass centered at this particular point. You can follow the laser pointer on the screen and open our compass up to the radius, which is 2 nautical miles, and draw a small arc. So you can see this arc coming up on the screen. This arc is having a radius of 2 nautical miles. Now what I will do is I will draw a tangent to this arc, which is parallel to my final course. So I take up my parallel ruler or set square or sliding ruler, align it with my final course, transfer it so that it is tangential to the arc. Let's now draw it. You can see this tangential line coming up on the plot. So we have this tangential line. This is parallel to my final course, and the distance between these two parallel lines is equal to the radius of my turn, which is 2 nautical miles. Now the same procedure is repeated on the initial course also. I pick up one particular point on my initial course. This is the point which is picked up. Now, keeping my compass centered at this particular point, opening it up to a radius of 2 nautical miles, which is equal to my radius of the turn, 2 nautical miles. I again draw an arc. You can see this arc also coming up on the screen. And now I draw a tangential line on this arc, which is parallel to my initial course. So using my sliding roller, set square or parallel ruler, I draw a parallel line tangential to this arc. So I can see the tangential parallel line coming up on the plot. Now you can see that both these parallel lines, the dotted lines, they intersect or join together at this particular point where the laser pointer is right now. And this point, let's name this point as C Charlie. This point is the center of my turn. This will be the center of my turn or the center of my curved path or center of my turning circle. So now what I do is I take my compass to the point C, the center of my turn. I take my compass to point C. Now we are aware that this point C is at a distance of 2 nautical miles from the initial course. You see these are two parallel lines, the initial course as well as the tangential line drawn on the plot. So the distance between them remains constant, which is 2 nautical miles. So point Charlie to my initial course is 2 nautical mile. I open up my compass equal to 2 nautical miles, which is the radius of my turn. And I now draw an arc centered at point C, which is the center of my turn. Radius equal to 2 nautical mile. I will draw an arc. You can see this arc now coming up on the screen. Now this arc will be touching my initial course. The distance between my initial course and point Charlie is exactly 2 nautical miles. And this arc will also be touching my final course. The distance between the final course and point Charlie is also 2 nautical miles. So this distance here, represented by the laser pointer now, is also 2 nautical miles. Now the points where this arc touches my initial course, let's name that as point A. And the point where this arc touches my final course, let's name that point as point B, Bravo. So we can see Alpha and Bravo coming up on the screen. The arc Alpha to Bravo basically represents the curved path which the ship will be following when it is altering its course from 010, that is my initial course, to 085, that is my final course. We now have the curved path which will be followed by the ship when the ship is altering its course. The curved path is obtained on the plot, or if this is done on the chart, you will have the curved path plotted on your chart. Now we are aware that if the ship has to move on this curved path and the alteration or the curved path has to start from point A, the rudder order has to be given or the wheel has to be put over slightly before this point. The reason for that is that whenever a helm order is given, the vessel takes some reaction time and it travels some reaction distance before which it starts to alter its course. The rudder order which is given is not implemented in the motion of the ship immediately, but it takes some time for the ship to react to that helm order. So the helm has to be given, the rudder has to be put over the reaction distance away from or before point A, point alpha. Now we are aware that in this question they have told us that the advance is known to be 4 cables. This is advance for 0 degrees, which is basically our reaction distance. So now as per my distance scale, I measure a distance of zero point 0.4 nautical miles from point A or before point A, and mark off that point. You can see this zero point 0.4 cables distance coming up on the plot as a green color line, and the point where this zero point 0.4 cable distance ends, I name that point as W. So this point W has to be my wheel over point. So you can imagine now the vessel approaching on the initial course 010. When the vessel reaches at point W, the helm is given. This is the wheel over point. So the wheel is given, the helm order is given. The vessel takes zero point 0.4 miles to react. So vessels travels from point W whiskey to point A alpha and takes this much time to react to the helm order. And once this reaction time or reaction distance is covered, after that the vessel responds to the helm and starts to move on the curved path. So we have the wheel over point on our plot now, represented by W whiskey. Also, you can see the angle which is made between these two lines, Charlie to Alpha and Charlie to Bravo. We have the curved path of the ship between Alpha and Bravo. Charlie is the center of the turn, and the angle which is made, that is Alpha, Charlie, Bravo, represented in yellow color in the diagram. This is the angle by which the ship is turning. Our initial course was 010, the final course is 085. So vessel is altering by an amount of 75 degrees. This angle here, the yellow color angle which you see represented by theta, this represents the alteration angle. So this is 75 degrees. Now moving further, we have the wheel over point on our plot as whiskey. Now, along with the wheel over point, another important item which should be there in all our planned turns is the wheel over line. And we know that the wheel over line always passes from the wheel over point and it is parallel to my final course. So my final course is 085. What I do now is I pick up my parallel ruler or sliding ruler, align it with my final course, which is 085, bring it to point W to draw a parallel line. You can see this parallel line coming up on the screen now, passing from point W, whiskey point, and parallel to my final course of 085. This line is my wheel over line. We are also aware that the wheel over line is very beneficial in cases where the ship has a cross-track error. So in case of any cross-track error, irrespective of whatever is the cross-track on the initial course, if you give the helm whenever you touch the wheel over line, you will always end up on your final course with zero cross-track error. So that is the advantage of the wheel over line. So we have the wheel over line now on our plot. Now we have one more method to obtain the wheel over line. Let's see the second method also. In the method which we saw, the method which we used, this is known as the plotting method. We first found out the center of the turn, then plotted the curved path on which the ship will be moving, that is alpha to Bravo. Then from point alpha, we plotted the reaction distance to obtain point W, and passing from point W, we draw a line parallel to our final course, giving us the wheel over line. Now the second method which we have is the calculation method. For that method, we don't need to plot the center. We don't need to draw the curved path. We don't need to know what is the alpha point. point alpha on our plot. Without plotting all these things, we can obtain the wheel over line. Now that is done using the formula r into 1 minus cos theta plus f sine theta. R in this formula is the radius of the turn. Theta is the angle by which the ship is turning. F is the reaction distance, and theta again is the angle by which we are turning. Now, if we put all the values as per this particular question, the radius is 2 nautical miles. So 2 multiplied by bracket start 1 minus cos of 75 degrees. 75 degrees is the angle by which we are altering, bracket close, plus 0.4. 0.4 is our reaction distance. It is given in the question, 4 cables. Sine theta, sine of 75. Theta 75 is the angle by which we are turning. So when we put all the values as per this question, we obtain a value of 1.87 nautical miles. Now, how do we use this distance? Let's use it on the plot. We come to the plot now, and on the final course, we pick up any suitable point. Any point of our choice can be picked up. I have picked up this particular point here. Now I keep my compass at this particular point where the laser pointer is right now. The compass is centered at this point. The compass is open equal to this distance which we have calculated, that is 1.87 miles. So this distance up to here is 1.87 miles, and you can see it shown here also, r into 1 minus cos theta plus f sine theta equal to 1.87 miles. And I draw an arc. If we draw a tangent to this particular arc, we will exactly get the same wheel over line which was initially obtained using the plotting method. So any of these two methods can be used practically. If you are interested in the center of the turn as well as the curved path, and you are making the curved path on the chart, this will happen in restricted areas where the ship's path is passing close to navigational dangers, shallow waters, restricted areas. So you would like to see the curved path on the chart. So in those cases, you can plot the reaction distance alpha to whiskey A to W and get the wheel over line easily. But if you are in deeper waters, open seas, and the curved path of the ship is and not required to be shown on the chart, in that case, you can calculate this distance using the formula r into 1 minus cos theta plus f sine theta and draw a line at this particular distance from the final course line which is parallel to it. So a line drawn at this particular distance parallel to the final course, which is in the direction of 085, will give you the wheel over line. Wherever this line cuts the initial course line, that will give you the wheel over point W. So if you use the calculation method, you can obtain the point W, whiskey point, as well as the wheel over line without doing any plotting on the chart. Both of these are independent methods. They are independent of each other, and any of them can be used as per your requirement. So we have now obtained the wheel over line, the wheel over point. Now in the question, they were asking us, determine the setting of your VRM of the radar to identify the wheel over point. Now this distance which we have calculated, 1.87 miles, is that value which should be used to set up a VRM on the radar. Now how will this VRM help us? When the ship is proceeding on the initial course and this 1.87 miles VRM is set up, as the vessel reaches point W, you will see that the VRM will touch our final course line extended backwards. So the VRM is going to touch the final course line. In some cases, you may need to extend the course line backwards. Now, as soon as the VRM touches the final course line, you know it is time to put the wheel over and commence the alteration. Even if you have some cross track error, let us say you are moving on this particular track, you can follow the laser pointer. If you have a cross track error, you are moving like this. Now, as soon as you come here on the wheel over line, this is the point where the VRM will be exactly touching the final course line. So wherever you are, irrespective of whether you have a cross track error or not, if you have this 1.87 VRM fixed up on your chart, fixed up on your radar, you know whenever this VRM touches your final course line or the final course extended backwards, it is time to put the wheel over and start the alteration. So we get our answer for part B of the question. So this is the setting of our VRM to identify the wheel over point. Now moving on to the third part, the current has been setting 315 degrees at a rate of 2 knots. Determine the new reference point for executing the turn. We will be giving a helm order. The vessel will be moving on a curved path. And during this curved path, it is not possible to counteract the current using the chart work techniques. Before point whiskey, before point W, we were moving on a straight line track. And moving on a straight line track, we are very much aware of how can the current be counteracted using the chart work techniques of counteracting the current using the course, speed and current vector triangle. So before point W, the current can be counteracted easily. And after the ship has reached point Bravo, again it starts to move on a straight line track. So after Bravo also the current can be counteracted easily using the chart work techniques. However, from point Whiskey going up to Alpha and going up to Bravo is the curved path, and we now need to know how do we counteract the effect of the current in this stretch of the passage. So for this, let us first calculate what is the total time required to cover up this passage. Now total time taken for turning after the wheel over point is given by, first of all, going from W to A Whiskey to Alpha. The total distance to be covered up is 0.4 miles or 4 cables, and the vessel is moving at a speed of 12 knots. So at a speed of 12 knots, covering a distance of 0.4 miles will take 2 minutes of time. So the vessel requires 2 minutes to reach from Whiskey to Alpha. That is the green color track on the plot. I'm showing it by the laser pointer. Now from Alpha to Bravo. Going from Alpha to Bravo, we are making an alteration of 75 degrees. Now when we are going from Alpha to Bravo, the speed of the ship is 12 knots. It is given in the question. The ship speed is 12 knots and the radius of the turn is 2 nautical miles. We know that the rate of turn is given by the expression of rate of turn is equal to V by R. V is 12 knots, radius of the turn is 2 nautical miles. So that gives me a rate of turn of 6 degrees per minute. So the vessel will be negotiating the turn at a rate of turn of 6 degrees per minute. The total alteration which is to be done is for 75 degrees. So the time taken by the ship would be 75 divided by 6. The vessel is altering 6 degrees per minute. So 75 degrees divided by 6 degrees per minute gives us a time of 12 and a half minutes. So vessel is going to take 12 and a half minutes to move on the curved path from Alpha to Bravo. The total time now comes out to be 12.5 minutes for the curved path between Alpha to Bravo, 2 minutes between Whiskey to Alpha, W to A, that is the reaction distance, total giving us 14.5 minutes. So we now know that from Whiskey to Bravo, the vessel is going to take a time of about 14 and a half minutes. Now let's find out the drift of the current for this time interval. We know the rate of the current is given as 2 knots. So with a rate of 2 knots in a duration of 14 and a half minutes, the drift of the current is going to be 0.48 miles. So we now know that the current is going to drift us in a direction of 315 for a drift of 0.48 miles. Now, how do we account for this current? Now, what I do is, let's come back to the plot. Pay your attention to point W. What I do is, I apply this current vector from point W in the reverse direction. Let me show it here. You can see this red color vector in the plot now. I have applied this red color vector. This is the current vector, the set and drift of the current. The direction is 315 and the magnitude of the vector is 0.48 miles. So this current vector is applied at point W in the reverse direction. Why have we applied it in the reverse direction? It will become clear to you in a while when we complete the plot. So the point where the vector ends is November. Let's plot it as November, call it as November. So November to whiskey NW represents the set and drift of the current. Now in the initial plot, we were giving our wheel over at point W. Instead of point W, if we give the wheel over at point November now, you see, if you give the wheel over at point November and you maintain the rate of turn of 6 degrees per minute, which is calculated as per our parameters, the current is going to take us from November to whiskey, and our rate of turn and the reaction distance is going to take us from whiskey to alpha and alpha to bravo. The resultant of both these vectors will be basically the course made good by the ship, or you can say the track, the curved track made good by the ship. So this November point which we have obtained now, November point, becomes our new reference point for executing that turn. So if we commence our turn at point November, the current is going to drift us from November to whiskey in 14.5 minutes. The rudder action of the vessel is going to take it from W to alpha, that is the reaction distance, and alpha to bravo if we maintain 6 degrees rate of turn as per our rate of turn indicator. So November to whiskey is the effect of the current. Whiskey to alpha to bravo is the effect of the ship's maneuvering, the rudder angle, the helm order, and maintaining a rate of turn of 6 degrees per minute. Take a course with zero cross track error. Now, when you are proceeding on your initial course, it is not necessary that you alter your course to reach at point November. We can now use the concept of the wheel over line again here. Instead of taking your ship to November, what we can do is we can now draw a wheel over line passing from point November. The wheel over line will be parallel to our final course of 085. So you can see this green color line passing from point November and parallel to our final course of 085. This line now becomes our new wheel over line. And when you are moving on your initial course, as soon as you touch this green color line here, this becomes your new reference point or new wheel over point. If you give the wheel over at this particular point, you will be reaching on your final track with zero cross track error. You will not be reaching at point Bravo in this case. You will be reaching somewhere onto the west of point Bravo here, but certainly with zero cross track error. If you had started at November, you will be exactly reaching at point Bravo. Now, since we have started little west of November, so whatever is the distance here, the same will be the distance between the point Bravo and the point where you hit your final course. Now, if you are in open sea, you don't need to go to point November and maintain this particular track. You can keep on following your initial course, and as soon as you touch your new wheel over line, the green color line, you can put the wheel over and you will see the vessel ending up on the final course line with zero cross track error. Obviously, the track will not be the one which is shown here in the plot, it will be different. So you will need to take care or monitor the progress of the ship if there are any navigational dangers, shallow patches, or wrecks close by. So that has to obviously be taken care of.